Okay, so these are the solutions to your differentiation test. There was an A part, a B part, and a C part. They were taken from different papers. So the A part that you did was taken from 2001. I think it was question 7A. If not, it was question 6A. So you're told taking x1 equals to 1. As the first approximation to the real root of the equation, you're told f of x, or we're going to say let f of x equal to x cubed plus x squared minus 1. That means that f dash x, or the derivative, is 3x squared plus 2x. A couple of you now got to differentiate the minus 1 and brought down the minus 1 for the derivative, so just watch out for that. Newton-Raphson formula, x2, which is what we're asked to find. So the second derivative, or sorry, the second approximation, x1 minus, I think it's a good idea to put this in a bracket. Sub in x1 into the f of x. Sub in x1 into the derivative. So start filling everything in. So that's going to be 1 minus, open your bracket, and you're finished. That's your 10 marks. The next part of the question, the B part, came from 1998. And it was question 6. And it was a C part. So you're given a function, f of x, and you're told that that's x over x plus 2. You're told x is an element of R, so that just means it's continuous. You're told x can't equal to minus 2. So straight away, really, they're giving you one of the asymptotes. They're going to give you the horizontal asymptote there. Anyway, we've to set about finding them. So, sorry, they give you the vertical asymptote there. So the vertical asymptote, fairly straightforward. You take the lower part of the reciprocal function, so that's x plus 2. You put it equal to 0. X is equal to minus 2. And that's it. That's your vertical asymptote done. Horizontal. Well, what you're going to do is you're going to get the limit as x goes to infinity of the entire function. So that's f of x. In other words, the limit as x goes to infinity of x over x plus 2. The problem with doing that is you'll end up with infinity over infinity, which is undefined, and we can't accept that. So in order to get around that, we divide across by the highest power of x. In this instance, the highest power of x is x, so we're going to divide each element, or each term, by x, and then we'll get our limit. So we're going to need a new page for this. So what I'm bringing forward is x over x plus 2. When I divide each part by x over x, all over x over x plus 2 over x. X over x, of course, is 1, so it's 1 over 1 plus 2 over x. And it is then this that I get the limit of. Now, of course, the 1 and the 1 will just drop down. There's no variable there, so there's nothing to sub in. It's this portion out here, or this term here, the 2 over x. There is a rule that says the limit as x goes to infinity of any constant over a variable will always go to 0. That constant can be 1, it's 2 in this instance, it can be anything. So what that means is that the limit of this is going to be 1 over 1 plus 0, which is just 1. So y equals 1 is the asymptote. So our two asymptotes, the y asymptote is y is equal to 1, and the x asymptote, x is equal to minus 2. That's the vertical one, and the horizontal one, y is equal to 1. Okay, next part of the question, you're asked, prove that the graph has no turning points or points of inflection. I'm going to call this part 2, even though it's not labelled in the question. So, f of x is equal to x over x plus 2. F dash x, using the quotient rule. Now I'm going to skip forward a little bit because you know I'm going to take it that you can do the quotient rule at this stage. You should be getting 2 over x plus 2 all squared. And the way you finish that off is you put that equal to 0 and you put a line through it. So in other words, the slope, which is your first derivative, if slope is equal to 0, sorry, just as a little aside, if slope is equal to 0, this is where turning points occur. So what we're going to do with this question is try and show that the turning point, or that the slope, can never be equal to 0. And if the slope is never equal to 0, well then there are no turning points. So taking it down again, so 2 over, if I try to solve something like that, I'd end up with 2 is equal to 0 times x plus 2 all squared. So 2 would be equal to 0, but we know 2 is not equal to 0, so therefore no turning points. You'll do something similar for the points of inflection. Points of inflection. Oh, sorry, need a new page. Points of inflection. They occur where the second derivative is equal to 0. So if we can show that the second derivative never equals to 0, well then we can show that there are no points of inflection. So f dash x, it was equal to 2 over x plus 2 all squared. F dash dash, or the second derivative, is going to equal to, and you'll just use the quotient rule again for this. Be a little bit careful when you're doing it. You'll end up with minus 4 all over x plus 2, x plus 2 all to the 4. Of course, though, lads, those x plus 2's can cancel. It's not essential that you do that now. Of course, you're going to use a similar thing, put it equal to 0. So minus 4, you can just take the jump, not equal to 0, therefore no points of inflection. And make sure you make that statement, please. Part 3 of the question. It goes on and it says find the range of values of f for which f dash x, that's the slope, is less than or equal to 1, where f dash x is the derivative. So basically do exactly as it says on the tin. You're told f dash x is less than or equal to 1. So I'm going to put my first derivative, less than or equal to 1. I'm going to multiply across by x plus 2 all squared. I don't need to flip the inequality. Because I know when something is all squared, that means it's positive, and the only time I need to flip an inequality is when I divide by a negative number or multiply by a negative number. So 2 less than or equal to, just dropping the 1 there because 1 into it is itself. Multiply it out. It's going to turn into a quadratic inequality. Now if you have a look at that, you won't be able to solve that using whatever method of factorization, etc. that you have. Your only option is to go straight into the minus b formula. So a is 1, b is 4, c is minus 2. So filling in the minus b formula, it'll be the square root of 16 minus 8, and remember it's all over 2, please. Minus 4 and there's your answer. But you have to remember, because you're dealing with a quadratic inequality, what you need to do is you need to sketch that down and get a look at it and see what's going on. So minus 2 plus root 2, it's still going to be a negative number, so it's going to be around about there, shall we say. Minus 2 minus root 2 will be a little bit back from it, not too far, don't worry about scale. It's a positive x squared, so it's going to look along those lines there. So what we have to go back to is up here, and we're saying, where is the curve greater than 0? In other words, where is it above the x-axis? That's this portion here, this portion here. So that corresponds to this area and this area. So the way we say that is x has to be greater than or equal to minus 2 plus root 2, and x has to be less than or equal to minus 2 minus root 2. You can combine those, of course. I'll just stick it here for you. The combination might not have space. No, won't combine it. Sorry. Okay, I'm going to stop and put the C part of the question onto a different video because I doubt I'll have time for it.